All right. You need to think all semester long, every time you take a measurement, you need to consider the uncertainties and write those down. We might have a table for you to write them down. Otherwise, you just need to find somewhere on your spreadsheet to write down the measurement and the uncertainties. One of the measurements you're taking today is resistance. And we're using an AM probe. And so you'll want to write that down. Resistance was measured with AM probe 37XR-A. In this particular measurement, I'm reading 7.5. And maybe you've seen that change to 7.4. That lets us know what the uncertainty is. With digital measurements, there's two observations you want to make. One is, what's the smallest decimal that it's reading? And secondly, how is it counting there? Some of our digital measurements don't count by ones at the smallest decimal place. Instead, they count by twos or even by fives. And so in this example, we would say the measurement was 7.5 and then plus or minus 0.1 ohms. That would be the uncertainty. To find the relative uncertainty, we would take the 0.1 ohms and divide it by 7.5 ohms and multiply by 100%. That would give us a relative uncertainty. Your post-lab is going to require you to write that down. Secondly, we have length as a measurement. Oh, and by the way, the resistance, again, for this experiment, you're going to hook the probes to the bolts, and this particular probe is not going to move for the rest of the experiment. You are going to take this probe off and move it to the next bolt and the next bolt. And even for the area experiment, hopefully this wire is creating a connection between all these bolts, so you can theoretically leave this probe right here. If you have to, you can move it to other bolts on this side, but theoretically you don't even need to move it after you've connected it. And it's not a bad idea to take a tissue or something and rub off that bolt, because somebody may have touched it with oils, and I've actually seen poor measurements because the alligator clip is touching oils and it's not allowing a good connection. Another measurement that you have is length. And again, you need to write that down and tabulate this. What is the measurement called? What is the sample measurement? Here we could just give one of these lengths. And then what is the uncertainty in that measurement? And this is an example where you have a 2-point measurement with some pretty serious parallax. You cannot touch the ruler to this washer. And so you have to eyeball it. And when you're eyeballing this, depending on where your eyeball sits relative to this system, you're going to get parallax. So that uncertainty on a typical ruler like this, you could say the smallest mark is 1 millimeter. The resolution is 1/2 millimeter. Because we can typically see if something falls in between two lines. So we could say 1/2 millimeter here and 1/2 millimeter here. And we would say that's because of the resolution of the meter stick. But we would not be representing the actual measurement very well. There's 3 questions we can ask when taking a measurement, if you remember from Lab 1. The first is, what's the resolution of the stick? And we've answered that. It's 1/2 millimeter. We'd have a millimeter uncertainty because 1/2 here and 1/2 here. The second question for uncertainties is, do I have any situation when I'm taking that measurement that decreases or makes the uncertainty worse? In other words, the interface or the interaction, when we take the measurement, do we have parallax? And in this case, we do have parallax. So that resolution of the stick, 1/2 millimeter, goes away. And over here, we can almost touch this end piece to our scale. So we might not have any parallax, and we could just use plus or minus 1 millimeter here. But over here we have a lot of parallax. And so you're going to have to decide, yourself and your lab partners, is that 1 millimeter uncertainty or 2 or 3 millimeters uncertainty? And so you'd write down length, sample value, whatever this is, plus or minus the uncertainty found from here and here added together. And if you wanted to state that as a relative uncertainty, you would add these two uncertainties up and divide them by the length measurement. That would be dimensionless and make it into a percentage. we need to write down each measurement. So resistance is equal to 7.5 ohms plus or minus 0.1 ohms. Or if you'd like, you can take this 0.1 and divide by 7.5 and multiply by 100% and write that percentage here. And then in parentheses, we'd say that this was the resolution of digital multimeter. So we've just written the name of a measurement, a sample value, and some students will give a range. They'll say 7.5 ohms to 33 ohms, and that's fine. And then plus or minus the uncertainty. And then you justify the uncertainty or explain how did you get this uncertainty. In this case, it was the resolution of the digital multimeter. The second measurement you have today is length. So length is equal to, and then we could write down, 30, it's not going to be 30 meters, because we are in meters here. 0.302 meters plus or minus 0.003 meters. And I would say over here, this is a 2-point measurement with parallax. So again, I've stated the measurement, a sample value, and again, you could do a range if you wanted to, plus or minus the uncertainty, and then I justified or told how I got that uncertainty. 2-point measurement with parallax. This needs to be done for every single experiment. The best way to accomplish this is to write this out while you're taking the data, because that's when that AM probe is turned on and you're seeing how it's counting, that it was at the tens place and it was counting by ones, not by twos or by fives. And when you're taking that length measurement, you can look at the parallax and get an estimation for the uncertainty. That's the essence of that post-lab question that will be on almost every single experiment. Oops, I forgot to give the punchline. You know, the final word, the finale. I also forgot to address the area as a measurement. So the finale should be, what about the uncertainty in rho? The resistivity cannot be known perfectly through measurement and calculation. There has to be some uncertainty in rho. We measured R, L, and A. Okay, area was found with a measured diameter, but what are the uncertainties in each of those measurements? How do they contribute together to give an uncertainty for resistivity, rho? We call this contribution of the uncertainties air propagation. We plotted R versus L over A. The slope was rho, resistivity. One way to find the uncertainty in slope is to add all the relative uncertainties that went into creating the plot. Remember, we cannot simply add uncertainties. We cannot add ohm, meter, and millimeter squared, but we can sum the percentages. So we employ relative uncertainties. Let's take resistance. Resistance is, in this example, 7.5 ohms plus or minus 0.1 ohm. The uncertainty related to the measurement is called the relative uncertainty. We take the uncertainty, represented here by delta sub r. Delta, this is a lowercase delta, meaning a small difference. The uncertainty in resistance divided by the resistance, and turn it into a percentage. In this example, it's 1.3%. So we could state the resistance as 7.5 ohms plus or minus 1%. Instead of a measurement uncertainty, which has units, we could state the uncertainty as a percentage. Relative uncertainty. How about length? Well, we have an example here of 0.211 meters plus or minus 4 millimeters. The relative uncertainty would again be the uncertainty divided by the measurement. And here we get 2%. So length has a 2% uncertainty, relative uncertainty. Now area. The area ranged from 0.030 millimeters squared to 0.200 millimeters squared, where the uncertainty is 0.002 millimeters squared. The uncertainty in area is twice the uncertainty in diameter. Diameter was measured with a micrometer whose resolution was 0.001 millimeters. That's a precision micrometer. Relative uncertainty in area, uncertainty divided by measurement. We get 2%. So when we add up the relative uncertainty in resistance and that of length and that of area, it gives us the relative uncertainty in resistivity. In other words, we get 5.3% relative uncertainty in resistivity turned into a percentage. Now let's say that my experiment yields a resistivity of this, 0.998 ohm millimeters squared per meter. Take note that relative uncertainty multiplied by the measurement, or in this case the experimental, would give a measurement uncertainty or an experimental uncertainty. I found the sum of relative uncertainties to be 0.053. Remember, it's dimensionless. And the measurement is 0.998 with dimensions. If we take the relative uncertainty, this number, and multiply it by the measurement, or the calculation, we will get the uncertainty as a measurement. The units transfer, and we get 0.052894, blah, 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 ohm millimeters squared per meter. But remember that uncertainties normally carry only one significant figure. So we don't need these significant digits here. We only need one significant figure. Rounding properly, we get the uncertainty in resistivity is equal to plus or minus 0.05 of an ohm millimeter squared per meter. Stated together, measurement with uncertainty is rho equals our measurement with units plus or minus our uncertainty with the same units. Uh-oh, do you see a problem? Do you see a problem with how I've stated rho? Look carefully. Is there a discrepancy? How well can we know this number for resistivity? Right here, it tells us how well we can know the resistivity, and it looks like, our uncertainty in resistivity is this number, 0.05. But we've stated the value of resistivity out to the 1,000th place. Can we really know the 1,000th place if our uncertainty is in the 100th place? I don't think so. We cannot know the value for resistivity to have a greater precision than that of the uncertainties. We can only quote resistivity to the nearest 100th, not 1,000th. Rounding this number, 0.998, to the nearest 100th yields 1.00 ohm millimeter squared per meter. Don't forget to use both the zeros, since they are both significant. Our final statement for resistivity experimental would be this. Rho equals 1.00 units plus or minus 0.05. If we find the relative uncertainty, which we already found because we summed the relative uncertainties, it's a 5%. Now, why use ohm millimeter squared per meter? Why not reduce simply to be ohm meter? Well, I personally like the visual reminder within the dimensions. I like those dimensions to reveal which physical properties were present. And I see resistance, length, and area when I look at ohm millimeter squared per meter. Nevertheless, simplicity might call for reduction to ohm meters. So let's quickly take both the measurement and the uncertainty and convert to ohm meter. If we take 1.00 ohm millimeter squared per meter, we notice that in 1 meter we have 1,000 millimeters. But since we have millimeters squared, we have to do that conversion twice. Millimeters and millimeters cancel with the millimeter squared, and this meter in the denominator cancels with this meter here, so we're left with ohm meters. This number simply becomes 1 times 10 to the negative 6th ohm meters. I'm pausing for a second. I made a mistake. There we go. Therefore, 1.00, it looks like I did it here, e to the negative 6th ohm meters plus or minus 5e to the negative 8 ohm meters. Well, how come we could do that so quickly? Well, we'll notice that right here is the decimal place for the uncertainty, the hundredths place, and that's 2 decimal places to the right. So this negative 6 simply becomes negative 8. And of course, we still have it stated as a percentage, 5%. Now, what about temperature and a table of resistivity? Let's make a quick word about temperature. Right here we have represented a cross-sectional area of a wire. And in here we've represented it rather crudely, just atoms. Okay, the current is going to travel through the wire using the atoms that are available within the wire. Those atoms have free electrons, and there's a pretty interesting process for that current to flow. We talk about paths of conductivity. Depending on the metal, it's going to change how many paths of conductivity there are and how I guess we could say easy it is for that current to flow. How difficult it becomes yields itself to the resistivity. Now, what happens to the atoms inside this metal as the metal gets hotter and hotter and hotter? Think about water. What happens with water to the water molecules when you heat up on the stove? It eventually boils and turns into steam, right? It goes from liquid to gas. That happens because of increased kinetic energy of the atoms. They're moving, they're vibrating and moving around more and more and more chaotically the higher the temperature. Well, you can imagine if current was trying to travel through this wire and all the free electrons are part of atoms that are screaming around this wire, okay, with excitement because of temperature, the resistivity would change. In fact, when temperature goes up, the resistivity also goes up. And conversely, if we cool this wire down, there's great work being done in getting to absolute zero. When we get down to really cold temperatures, all these atoms start to slow down, and the resistivity can go to zero. In other words, theoretically, when there's no temperature, when we're at 0 Kelvin, we can have zero resistance because resistivity has gone down. In other words, conductivity has shot sky high. So really, when we're talking about a final resistivity for nichrome wire for this experiment, what we should be saying somewhere is this was done at room temperature. If we look at a table of resistivity, this particular one, there's probably tens of hundreds of them, thousands of tables of resistivity you can find. This particular one was at, let's see here, Wikipedia. Electrical resistivity and conductivity. And scrolling through here, we can see nichrome. And look, the expected value of nichrome is 1.1 times 10 to the negative 6th. But what are the units being used? An ohm meter. And here it says at room temperature, at 20 degrees Celsius. You can take a gander at some of the other metals that you might be familiar with. We've talked about copper. Gold has a higher resistivity than copper. The reason that gold is often used on connections for audio connections at the tip and for HDMI and all these other things, they use gold plating, not because it has a lower resistivity, because it doesn't. Gold has a higher resistivity, meaning higher resistance. The point of using gold there is that it, I'm losing the word here, that there's not a degradation in the metals, the corrosion. There's the word. It corrodes less easily than copper does. Here's aluminum. We had mentioned that in one of the movies about how aluminum has a higher resistivity than that of copper. You can see how much higher it is. And aluminum wire can cause fires in houses if you're not careful. And then way down here was, well, look, there's glass, sulfur, air. Look how large that resistivity is. So remember, resistivity is a property of the element that hinders the flow of current. It's the inverse to conductivity, how much the property of the element that allows the flow of current. I hope you've enjoyed this experiment, and hopefully you can gain something from this thought about uncertainties and how errors propagate through the calculations to give us a final uncertainty in our conclusive resistivity.